We have to speak in English because we have to record. So, last time we discussed the choice of the behavior factor for timber structures, and we said that for cross-line buildings, basically, let me just like this. Okay, so this is the table that we can take from our Italian regulation in order to choose the behavior factors. So we have to make a distinction between high activity and medium activity, and we found out that for the most important systems, for example light frame construction, we have a value ranging from 3 for the activity class medium to 5 for the activity class high. While instead for cross-laminated timber buildings, our Italian regulation provides only one value, 2.5, which is for the activity class medium. We also said that, strictly speaking, if we have a type of cross-lam building characterized by short walls with vertical joints, then, based on some tests that were carried out in Japan by Italian researcher, Professor Fragiacomo, he concluded that we can use a Q factor of 3, while instead, if we have walls without these vertical joints, so walls as long as the whole wall, I would say, so a panel as long as the whole wall, in this case, we should use a behavior factor of 2. The Italian regulation doesn't make this distinction, it just assumes Q equal to 2.5 irrespective of the type of wall. So in both cases, Q equal to 2.5. But in the new Eurocode 8 that we are revising right now, there will be this distinction between those two systems. So Q equals to 2, this will be the activity class medium, while instead the other one will be the activity class high. So, another important thing is about regularity in elevation. This is something that you will learn more when you will attend the timber earthquake engineering course. Sorry, not the timber, the earthquake engineering course. The idea is that if we have a building which is not regular in elevation, so for example we have a change in stiffness and mass as we go to the highest floors, in this case, the Q value listed in the table should be reduced by 20%. In any case, there is the minimum value of 1.5 that we can assume in any case. So, for example, in your design that you are doing for your single story activity, you are designing as a low dissipative system. In your case, you are going to use a Q equal to 1.5. Okay, so not 1 or not a different value. 1.5, you design as a low dissipative system, as we discussed, in order to make it similar. Now there's a very important point here. If you look at this table, we go back. In this table you will find that those are the maximum limits of the behavior factor. So this is the upper limit, it's not the default limit, this is the upper limit. And then we will find that the regulation said, particularly Eurocode 8 said that in order to ensure that the given value of the behavior factor may be used, for example, 2.5 for X-lam, or 5 for right frame, the dissipative zone shall be able to deform plastically for at least 3 fully reversed cycles at a static activity ratio 4 for the activity class M, and a static activity ratio 6 for activity class H structures without more than 20% reduction of their resistance. So what does it mean, this paragraph? It means basically that, first of all, we should be able to identify the dissipative zones. So this is the most important thing, right? When you are designing your reinforced concrete frame, the first important thing is to understand what are the dissipative zones. So first we would have to decide here, or to define what are the dissipative zones. And then theoretically, we should perform some tests, some cyclic tests. And fully reverse cyclic test, what does it mean? For example, if I define, if I have a wall, and if I define that this is a For example, the connection of this wall to the foundation is a dissipative connection. What I should be doing, I should basically apply a load, for example, with a jack here. So with a jack, I should basically move the free end of this wall, so move in one direction, in the other direction. Okay, I should move this according to a certain loading protocol, which means that. So suppose that this is Q, so this is the horizontal displacement. So there is a regulation saying that when we want to test for cyclic resistance this dissipative connection, what we should be doing, we should move forth and back this free end from a certain quantity. So for example, this is the displacement, this is the imposed displacement by pulling and pushing the free end of this wall using a jack. You should have 3 fully reversed cycles, so this is the time, and this is the lateral displacement on top of the wall. So we should push this way. Okay, so actually pulling this way, then push, fully reverse load 3 times. So 1, 2, 3, and then we should move to a larger target displacement, and then we should increase in this way. So this one is the history of the top displacement of this wall over the time. So we should start with some, let's say, small displacement. So if I have this, for example, this is my wall. First I'm going to move the wall in this direction, then the other direction, then again, 1, 2, 3, 4, 5, 6, and then I'm going to move it more and more. Continue this way, always 3 times. Okay? And then I increase the displacement always 3 times. When I end up the test, I'm going to end up the test when there is some failure somewhere around. And I'm going also to plot the applied force. So here you have an applied force versus displacement. So this is the applied force versus displacement. And I'm going to show you, you will get some cycle like this. Then we increase. At a certain point, you will see that this is going to reduce. And what we have, if you do the envelope of this peak, you're going to have a decrease. So, the regulation in some way said that in order to be able to use these upper limits of the behavior factor, theoretically, we should be doing some cyclic tests like this first by identifying the dissipative zones. And then by testing the dissipative zones in both directions. So this is a fully reverse. It's called fully reverse cyclic loading, because you see that first I move the wall on the right for a certain displacement, and then I move the wall on the left for the same displacement, so forth and back. So loading and loading and so on. So every time 3 times. So the regulation said that I should continue. And if I have a mid-activity class, so in mid-activity class, this decrease, you see that there is a decrease here. So this is a delta F in some way. I get to a certain point when you see I have a decrease, delta F, like a kind of softening. So this decrease should not be more than 20%. So delta F over F should be less than 20%. So this decrease here, delta F over F max. Let's say this is F max, so delta F over F max should be less than 20%. For an activity ratio of 4 for medium activity class, or 6 for high activity structure. So in some way, so if this F and U, and if this dashed line is the envelope of this cyclic test, I will have then to find out an equivalent kind of elastoplastic relationship, which is actually, to be honest, it's not an equivalent, it's more a kind of bilinear relationship, something like this. So this is the conventional yielding point. And when I get to a point where I have here a decrease, so F max, this is delta F, so delta F equal 20% of F max. So here I identify this is U Y, this is U ultimate. So mi, this is the activity ratio, so it's U ultimate divided by Uy. This shall be greater than or equal to 4 for the activity class M, and 6 for the activity class I. Now let's try to repeat shortly again about this. So we said that the regulation said we can use the upper limit of the behavior factor given in the table when I have performed some fully reverse cyclic loading, cyclic tests on the dissipative zones. These fully reverse cyclic loading are characterized by 3 cycles, so 3 in one direction, 3 in the other, with increasing amplitude, as you can see here. Once I've done this cycle, I'm going to approximate, I'm going to find what is called first Beckman curve, curva in gruppo. So this first Beckman curve is a curva in gruppo of the peaks of these cycles. And then I'm going to approximate this first Beckman curve, this curva di sviluppo, with a bilinear curve. So this is a bilinear curve, bilinear, passing through a conventional yielding point here. On this equivalent bilinear line, I'm going to stop where I have a decrease of the peak force, F max, equal to 20%. So I'm going to define, this is my convention, this is the ultimate point of my structure. So this is the yielding, conventional yielding point. And this is the conventional, those are both conventional collapse point. I measure the two values of displacement, Uy and Uu. So Uy is the displacement associated to the conventional yielding point, and Uu is the displacement associated with the conventional collapse point. Then I do the ratio. The ratio will provide me what we define as a ductility ratio. The ductility ratio shall be not less than 4 for ductility class medium, and not less than 6 for ductility class high. Okay? So only if I comply with this relationship here, I can use the upper values. I can use these values here coming from this table, okay? Because those are upper values of the Q factor. So now, in order to understand how to do it, because of course, when we design a structure, we can't every time do experimental tests, so we need to find out some simplified way to solve the problem. The first important thing to solve is actually to understand what are the dissipative zones for the different structural systems. So, to understand what are the dissipative zones for across lambda, we can have a look to this video, which depicts one of the tests that were carried out in Japan on this 3-story cross-laminated timber building by Professor Ceccotti. So this is a shaking table test. So as you can see here on the base, this base here, it's a base that can be moved all around with all degree of freedom in space, and can be moved with the same acceleration that you want. So in this case, what they did, they built this building out of crosslamp, and then they subjected this building here to basically an acceleration that was recorded during some past earthquakes. Now let's have a look to the video and let's try to understand what kind of dissipative behavior we can see. Okay, let's try again. Let's look at the wall. If you see, this building is made from different panels, short panels, and during the earthquake, as you can see, there is a kind of very clear dissipative behavior. If you want very clear displacement, look at this wall and look how it rocks on one side and the other. So in the end, the idea is that in a building like this, the dissipative behavior is rocking toward one. So each rectangular panel making the wall during the earthquake is going to basically rock rigidly. Rock means not density, of course, it's not rock. Basically, it's like a kind of density one. The wall is going to rotate rigidly around the corners, basically. So, if this is a wall made by two panels joined, you see, along the vertical side and connected to the floor with some hold-downs and the brackets, the kind of behavior that should occur during an earthquake in order to make some dissipation of energy is the one that you can see right now. So if I apply horizontal force, the two panels should be able to rotate rigidly around the corner. Okay? So this is the kind of dissipative behavior typical of cross-laminated buildings. Now, in order to ensure that this kind of displacement can occur, what kind of connection should be able to plasticize? Now, if you look at this connection here, in order to make sure that this behavior can occur, what kind of connection, in your opinion, should be able to plasticize? So, let's try to have a look. For example, this connection here, made with, for example, LVL, a strip of LVL with some screws. Do we need this connection here to plasticize in order to ensure that the wall can rock? In other words, how should we design this connection here? To remain elastic or to plasticize? In order to make sure that the whole wall can rotate and can dissipate energy as in accordance with this sketch here. So, Waiting for some comments. So, how are you going to design this connection here? As a dissipative connection, in order to plasticize, or as a rigid, or let's say as an elastic connection? You see, why is it? If I were to design this as an elastic, non-dissipative connection, what kind of deformed shape I would get? Okay, if this one was, let's say, was not plastic, so was over, in some way was, if this connection was over designed, was very stiff, what would it happen? What would be the deformed shape of these two walls? So it will, I mean, what do you mean? Would it be able to rock or not? But suppose that this is rigid. Could it rock or not? Who affects the rocking behavior of the? I mean, it's only this, or there are also the other connections. Suppose that I design this as a glued, fully rigid. What would be the deformed shape of this? The whole panel would behave as a rigid one. So I would have a deformed shape like this. Right? Okay, so if I want to have a deformed shape like this, the only way, either I don't put any connection here, or if I put some connectors, those connectors should be able to plasticize. So the connection should be sufficiently weak, okay, soft. Because if I put this one as a rigid, then I get a behavior like this. So in this system here, let's see it again. As you can see, look here. So this connection here, is it rigid? No, because if this connection here and here they were fully rigid, then we would see the rocking of the whole wall. Instead we see the rocking of the separate part. Okay? So, first of all, we need to make sure that this connection, like we already said before, this connection should be able to plasticize. Because if this connection is too rigid, so it doesn't plasticize and it remains elastic, then I would have the rocking of the panel of the wall as a whole. Okay, without any relative displacement. So first important thing is make this connection able to plasticize. Now, is it the only one that should plasticize in order to have the rocking of the wall? No. Which other connection should be? Let's have a look down to the all down. The all down must allow, you see, this uplifting of the wall. To allow this uplifting of the wall, the all down should perform plastically. Now, the all down is made of a piece of steel, a bolt here, the foundation, and a nail connection between the all down and the wall. Which one of those three connections should be able to plasticize? All of three, or is better one or the other? So there is like a bolt here, then the plate, and then there is this nail connection between the plate and the timber. Now, if we have a plasticization of the bolt in the foundation, we risk that we have basically a tensile failure. And once we have a tensile failure, what's going to happen? This system become statically unstable. And so then we cannot have everything anymore. Same problem with the plates. The plate could also plasticize in tension, but then, of course, the hold down wouldn't be able, so the wall wouldn't be able to go back to the initial condition because it would be this kind of plasticization. But anyway, there would be a risk of brittle failure because this plate is subjected to tension. So, what should really, the only thing that should plasticize here is the nail connection between the plates and the wall itself. So, this one, this nail connection between the hold down and the wall should be able to plasticize. And if you remember, see, this is a nail connection, and the nail connection is characterized by, let's say, a ductile failure only if the nail itself is not plasticize. We will need to make sure that the failure mode of this steel to timber connection is characterized by the formation of 1 or 2 plastic hinges into the nails. Okay? There's not enough that this plasticized. In order to make this to plasticize, we need to make sure that among the different failure mechanisms that we found for a nail, for a steel to timber nail connection, we have these failure mechanisms characterized by at least the formation of 1 or 2 plastic hinges into the nail. Same thing on the angle brackets. Also, the angle brackets should be able, you see, to plasticize, because otherwise, if this connection does not plasticize, it cannot allow for this uplifting of the wall itself. So all these nail connections between steel plates and timber should be able to plasticize. Plus, we set this groove connection here between the 2 walls. So again, if this is you see better the hold-down construction, this in red, this nail steel to timber nail connection should be able to plasticize. This screw connection between adjacent wall panel should be able to plasticize. And this nail connection between the steel angle brackets and the wall should be able to plasticize. Now, we go back to this regulation that we were discussing before. There is a special regulation dealing with the cyclic tests of dissipative connections, this EN 12512, which is entitled Timber Structures Test Methods, Cyclic Test of Joints Made with Mechanical Fastener. Now you can see better what I was meaning before. So this is V. Well, V is what I call U actually, it's another symbol. So the idea, as you can see here, we have to do 3 fully reverse cycles, then to increase until we get to the failure. This is the procedure. This is a typical example. This is a test that was carried out on the groove connection between 2 adjacent panels. And you can see in blue, these are the cyclic tests. You can see that due to the fact that we repeat 3 times the test at the same displacement, we have a degradation of strength. So when we get, for example, here, then we do the whole cycle, we repeat again, we get back to the same displacement, but now you can see that the next time we have a reduction, we start from here, then we do the whole cycle, we go back to the same displacement, next time we get here. Then we do again the whole cycle, we get back here. So we have a degradation of strength. We have strength degradation from one cycle to the other. This is strength degradation is typical of timber structure. As well as this shape, which is called pinching. This rounded shape is called pinching. Also, this is typical of timber structures. So this is a way to carry out the test, the one that I said before. This is a reaction frame. A wall, for example, a cross-line wall, which is connected to the foundation with some hold-downs and the brackets, and then with the horizontal actuator, we apply some horizontal displacement. This is a test, and this is at the end of the test. You can see here we have some plasticization of the nails, of this between this angle, between this hold-down and the wood. There also plasticization of these nails between the undergrads and the wood. It should also be noted that usually at the end of the test like this, the cross-lamp panel does not appear significantly damaged. So all the damage is concentrated in this connection here. And this is the result of this test. You can see if you, well, actually, if you need to remember, the area which is included within these loops of colors is a measure of the energy that has been dissipated by the structure during an earthquake. So why do we test our structure with some cycles of load? Because usually the earthquake is characterized by cyclic loading. So your structure cycling in one direction, in the other, and so on. So that's why we perform a cyclic test. And we are very interested in seeing the shape of these loops, which are called hysteretic loops, hysteresis. And the area within these lines, it's a measure of the energy dissipated during the earthquake. So the larger the area, the greater the dissipated energy. And the greater the value of the behavior factor. So if we have a structure which is going to dissipate a lot of energy, this structure will be characterized by fat loops like this. And then we will be able to use a higher value of the behavior factor. Instead, if we have a structure, for example, characterized by hysteretic loops like this, in this case, the hysteretic, well, the loop are very slim, so the area within the loops is very small, and so will be also the behavior factor. So in a structure like this, the behavior factor will be very low. Well, instead, if we have lots of dissipated energy like here, we can use a higher value of the behavior factor. Okay? So from our point of view, if we want to perform a better seismic design, we are looking for behaviors like this. Okay? Not like behavior like this. So, it is interesting now to notice that despite the fact that, if you remember, wood itself, it's not a very dark material, because wood itself, if you do a test on the wood itself, like a bending test on the wood, you will get something like this. You wouldn't get any energy dissipation. However, if they design the wooden structure using some steel connections, and if I make sure that the steel connection dissipates energy, so the steel connection, like this nail connection here, are characterized if this is the all down, for example, and this is the panel. If this nail connection is characterized by the formation of 1 or 2 plastic hinges, okay, then obviously not something like this. So if this is the all down, not pure embedding. So if I have a behavior like this with 1 or more plastic hinges in the nail, then you can see that in the end I can get a fairly highly dissipative structure where we have a fat hysteretic loop, and so I have a lot of significant amount of dissipated energy, and then I can use a behavior factor which is not very low. For example, for X I can use a behavior factor of 2.5 or 3. Okay? So, we can conclude X wall panels can dissipate energy and behave in a ductile manner if the connections plasticize. The X panel itself do not contribute to the energy dissipated shown by the failure. So in other words, if I do the same test, on a cross-lamp panel which is glued on the foundation, I do exactly the same test, I will get something like this. Okay? So everything is related not to the cross-lamp panel itself, but rather to the connection itself. There is a significant strength degradation from the first to the second cycle and reduced strength degradation from the second to the third cycle, and remarkable strength increase after the yielding. So after the yielding you have a significant, you see, increase in strength. It's what we call overstrength that we have to decide, we have to discuss today. If you remember also for retroscopic you had overstrength, but as we said last time, while for retroscopic the overstrength factor was, some of you were telling me, was 1.2, 1.25, you will see that here instead the overstrength factor will be 1.6, will be much higher. Okay? Now, how do we calculate this conventional yielding point? The problem, when we talk about timber, the problem is that unlike steel, if you do a test like this and then we do the envelope, we will never find a typical or it's very seldom we will find a curve like this. So the typical curve with the yielding, so the typical bilinear, we will always find a curvature here. Now, if we can approximate, like in this case, quite well the curve with a bilinear one, then the yielding point can be found this way. You see, by taking a tangent here, so the intersection is the yielding point. However, very often, most often, when we construct this backbone curve, we will end up, you see, with a curve like this, completely curvilinear. Now, if we have a completely curvilinear backbone curve, we need to make some kind of assumption in order to find the yielding, the conventional yielding point. And the assumption made by this regulation is that the first branch is obtained by taking the secant curve from 10% of max and 40% of max. You see here there is a secant curve here. And then the second one is tangent with an inclination 1/6 of the first one. So if you want, this is a pure conventional construction in order to get this conventional yielding point. Okay? So we have to do this pure conventional construction, get the yielding point, and then we need to define the ultimate point. How can we define the ultimate point? The ultimate point, you see, is the value. If you look at the ultimate point, it can be determined by 3 criteria, not only one. Before I was talking about 20% just for simplification, but actually there are 3 criteria. The 3 criteria are that we get to the actual failure point. What could be the actual failure point? For example, you are testing the wall. At a certain point, you get a failure of the hold down. If the hold down fails in 2 pieces, then you get to this point here, and then the card is going to go down vertically here. So you get basically a failure here. Or you can have a reduction of the backbone by 20%. Or they said, if the displacement becomes too big, for example, 30 millimeters deep, then we should basically stop the test. So we have these 3 criteria. So the failure is defined by the criteria which occurs first. Okay? If you want, this is just a conventional way, again, to define the ultimate displacement. Why do we need the ultimate displacement? Why do we need the yield displacement? Because you need to be able to calculate this ductility ratio. Remember for steel, we calculated in reinforced concrete the ductility, the curvature ductility ratio for reinforced concrete section. So we have to calculate the curvature of ultimate. We say the curvature of the yielding point. In that case, they were easier to assess. In this case, we need to calculate the yielding point and the ultimate point in a kind of conventional way. We can then calculate, you see, this ductility ratio between its ultimate value and the yielding strength. So, if μ is greater than 4, then we can say we have a medium ductility class, DCB according to NDC 2018. If μ is greater than 6, we have high ductility class. So DCA according to NDC 2018. Okay? So to understand where we are, if we have ductility class mean or high, we need to perform those tests on the dissipative connections. So, for X-lam construction, we found what are the dissipative connections. Now, the question is, What are the dissipative zones for light frame construction? For light frame construction, only the shifting to frame nail connections on the perimeter are regarded as dissipative zones. Okay? So in light frame construction, only the nail shifting to frame connection is regarded as a dissipative one. So this connection that is depicted in red in this drawing is the only dissipative connection. Everything else, all the other members, will have to be over-designed for the dissipative zones. Okay? Again, if we do a test like before, a cycling test on a wall, where we make sure that only the nail connection on the perimeter of the wall dissipate energy, again, you see, we will find this kind of high strength. Again, those high strength look, as you can see, they are quite fat, meaning that the structure is able to dissipate energy, and meaning that we can use a significant value of the behavior factor. According to the Italian regulation, if you are in a high activity structure, you can use a behavior factor of Q equal to 5. Very high. What was the value that you used for your reinforced concrete frame? Five. So, they're always watching. 5. Here we are talking about 5, more or less the same. It's a very high value because if just a reminder that you get 5, you have to put lots of stirrups, and you have to make sure that the cross section was under reinforced, because otherwise you don't get so 5 also for timber is a quite significant value. And basically the idea, you see, that we should have this kind of behavior. So only the dissipative connection on the perimeter of the sheathing should plasticize. Everything else should remain elastic. If this is the case, we can get a good dissipative behavior. So, according to Eurocode 8 and the Italian regulation, a Q factor of 5 may be assumed. Note that some other regulations, like the Lucina standard, and also the new Eurocode 8 that we are going to issue later on, will reduce this value from 5 to 4, because we found that 5 is a bit too high. Okay? For the time being, you can use 5, but just be aware that the use this will be reduced to 4. So in my opinion, it wouldn't be a bad idea to, since 5 is the upper limit value, it's the maximum, wouldn't be a bad idea also now to design the structure is to use 4, okay, instead of 5. Of course, down for both X-lam and light frame, we will have to design the dissipative connections using the design spectrum. Which means that for cross-lam, just remind, for cross-lam you will use the design spectrum to design, we say, the screw connection between the adjacent panels, the hold down, the connection between the hold downs and the panel, the net connection between the angle brackets and the panel. All the other components of the X-lam structure will be designed using capacity-based design. Okay? For light frame structures, you will be designing the nail shifting to frame connection using the design spectrum, the one with Q factor of 4 or 5. while everything else will be designed, all the other members will be designed using capacity-based design. Okay? In other words, to make a parallel with what you are perhaps more confident to do so far, which is design of a moment-resisting frame made of reinforced concrete. In the case of the moment-resisting frame made of reinforced concrete, you design the beam. Actually, you design in bending the beam for the design spectrum, so the one that you obtain by using Q factor of 5. Then everything else, so for example, the shear of the beam, the nodes, and the columns, were designed using capacity-based design. Okay? In this case, you'll be designing, if you design cross-stability, you'll be designing only the screw connection between the adjacent panels and the nail connection between the hold downs and the panel, and the nail connection between the undergraduate and the panel using the design spectrum, where you have used a Q factor of 2.5. Everything else, cross-lamp panels and all the other connections, will have to be designed using capacity-based design. For light frame construction, if you go back, this is the only component, so only the sheathing to frame connections with nails will be designed by the design spectrum using Q factor of 5 or 4. Everything else, including the hold downs, the frames, the sheathing, and so on, will have to be designed using capacity-based design. Okay? So we will need to learn how to use capacity-based design also for timber. So we have some requirements when we do a seismic design. For example, we have to use materials, mechanical fasteners with low cycle fatigue behavior, and sheathing material, she was a diaphragm, must be made of plywood, at least 9 mm thick. If you have this, you will learn also better this in your earthquake engineering course. So if your structure is regular in elevation, first of all, if your structure is regular in elevation, then you can use equivalent static analysis. If it's not regular in elevation, you use dynamic analysis. Now in this course we are just going to use equivalent static analysis, the one that you saw with Dr. Somenta, that you saw also with Professor Vitali. Okay? So we will assume that our building is regular. Of course, your building may be made by different lateral load resisting systems in the two directions, like in the case of reinforced concrete. You remember, you could have walls in one direction and frames in the other. If the building is regular, then you can reduce your seismic analysis to two plane analysis, one in one direction, one in the other, using different factors. Okay, you don't need to use the spatial analysis. Same thing we will do in this course here. So we will assume that the behavior factor is the same in the two directions. Okay? Or anywhere we could consider as a plane structure in terms of multi-story building. So now, if you remember, before we said, okay, we have a table. We have a table with the value of the behavior factors. Those behavior factors are the upper limit. If we want to use the upper limit, we need to make sure that the ductility of the structure is at least 6. If we want to use the upper limit of the value for high ductility structure, we need to make sure that the value of the ductility is at least 6. If we want to use the upper limit of the value factor for mean ductile structure, we need to make sure that the ductility factor is at least 4. The problem is that when we design, of course, we cannot check the ductility 4 or 6 by doing some tests. So the regulation provides some clauses that are similar to apply in the design stage. So the regulation said that these provisions of 3P may be regarded as satisfying the dissipative zone or structure type if the following provisions are met. In double, bolted and nailed timber to timber and steel to timber joints, the minimum thickness of the connected member is 10D and the fastening diameter D does not exceed 12 mm. What does it mean? It means that if our dissipative zone is made in this way, for example, so we have a double connection between two timber members and another timber member, if we define as T the thickness of the minimum timber member and D the diameter of the double, in order to be able to use the higher value, the upper value of the behavior factor, we need to make sure that T, the thickness of the minimum, so the minimum thickness of the timber member shall be greater than or equal to 10 times the diameter of the fastener, and the diameter of the fastener does not exceed 12 mm. So as you can see, without doing any experimental test, we can check this provision. These provisions are satisfied, then we can say, okay, we can use basically the upper limit of the behavior factor provided in the table we saw before. In shear walls and diaphragms, the sheathing material is put based with a minimum thickness of 4D when the net diameter D does not exceed 3.1 mm. So if we are now in a light frame construction, if you remember, there is a sheathing made of timber connecting with screws or nails to a frame. So in this case, if the thickness of the sheathing is greater than 4 times the diameter of the nail, and if the diameter of the nail is lower than 3.1 mm, we can assume, we can use the higher value, the upper value of the behavior factor table for high dissipative structure, so the value of 5. There is also another clause saying that if the above requirements are not met, but the minimum member thickness of 8D and 3D is assured instead of 10D and 4D, we can use some reduced upper limit values. So this means that, for example, in this case here, if T is not greater than 4D but is greater than 3D, and if you want to add, this I added before, if T is always less than 3.1 mm, then we can use a behavior factor of 4 instead of 5. So if the red condition is satisfied, we can use a Q factor of 5. If the blue is satisfied, we can use a Q factor of 4. Now here, you see, before we had T greater than 10D. With T greater than 10D and D less than 12 mm, the behavior factor was 3. If now instead, actually it was, no, it was not, let's go to 3, it was not 3, I think it was 5. Let's go to 6. Actually 4, if I remember right, it should be 4. Go back to the table. Remember where it's 4. Yeah, 4. 4 to 2.5. Okay, so if these conditions are satisfied, then we can use the behavior factor Q of 4. If these blue conditions are satisfied, if you compare the blue with the red, you will see that T is always less than 12 mm, but this time T is greater than 8D, not 10D, then Q factor of 2.5 can be used. Okay? So in the end, when it comes to design, for example, a non-resisting frame or light frame construction, you can check if you can comply with either of those one or the other one we saw before. If the two is satisfied, then you will use a behavior factor of 4. If the red is satisfied, you will use a behavior factor of 5 for the light frame construction. Okay? Now the question is, why do we need to check those ratios? So why, if, for example, T is greater than 4T and T is less than 3.1 millimeter, we can use a Q factor of 5. Otherwise, you only get a factor of 4. Because basically, those relationships are related to the type of failure mechanism. So, suppose now that we are going to calculate using the Johansen equation, the strength, the shear strength associated with this 4 failure mechanism. So the Johansen equation and this equation you can see here, for example, in this failure mechanism here for crushing, you can see that the characteristic shear strength is basically related, it's linearly dependent on the thickness T1 of the timber band. What is that? Failure mode J, which is characterized by formation of one plastic hinge, is non-linearly dependent upon T1, because we have one T1 here, and one T1 square underneath the square root. And if the behavior factor, if the failure mode is characterized by 3 plastic hinges, here there is an even more complex dependency upon the absolute, there's a simpler dependency upon the thickness T1, because you see here there is no T1, so this means that this one is constant basically, T1. So we can plot FVRK versus T1, where T1 is the thickness of the metal. So failure mode G and H are characterized by a linear dependency of FVRK over T1. Then there is this failure mode J, characterized by one plastic hinge, which is characterized by a non-linear dependency. And last, the failure mechanism characterized by 3 plastic hinge. Here, there is a constant dependency. Now, if we want to dissipate more energy, remember before, if we want to have a fat car, we need to dissipate more energy. To dissipate more energy, the only way we can dissipate more energy is to have one plastic hinge formation here, or 3 plastic hinge formation to the down. So the only way that we can dissipate more energy is to impose the plasticization of the fastener. So basically what we want to avoid in the dissipative region is this failure mechanism here, characterized by only crushing, only bedding. If we want to get to 1 plastic hinge formation or 3 plastic hinge formation, you can see we need to increase T1. So this is why there is this limit of T1. So T1 over D must be greater than this value that we found before. Okay? So in the end, this relationship here, this one, T greater than 4D or T greater than 3D or T greater than 8D, comes from the fact that only by imposing those limits, we can make sure that there will be, so only by using some standard, because in the end you see, T greater than 8D, it means that the fastener becomes very slender. So the slender the fastener, the easier is the plasticization of the fastener, because it becomes more slender. Another possibility, which is given by the new technical regulation, Italian technical regulation, that will be also in the future approved also in the Eurocode, in the Eurocode 8, is basically to ensure viable ones in the equation that the failure mechanism is characterized by one or two plastic information in the fastener. In other words, in general, without any limitation of the diameter, for example, on the fix of the timber member, if we have, for example, for a timber-to-timber connection, we may have 6 failure mechanisms. The idea is that if we have a dissipative connection, we should not allow any sort of failure characterized by no plastic hinge formation into the fastener. So the first 3 failure modes should not be allowed in any dissipative zone. The second 2, D and E, should be allowed in dissipative with Q factor of 4, and only the 6th, the F, should be allowed in very dissipative failure mechanism with Q factor of 5. So, when we design a dissipative connection, basically, we should make sure that we have either one plastic hinge formation, Q factor of 4, or 2 plastic hinge formation, Q factor of 5. Of course, we need to make sure that there is some difference, some sensitive difference between this failure mechanism, so the dissipative failure mechanism, and the non-dissipative failure mechanism. What does it mean? Suppose that you calculate the 6 values here. You use, for example, this formula here. You find out that, for example, let's say A is. Okay, let's do this. Let's write it, otherwise it's a bit more difficult. So, suppose we have this kind of connection, and we calculate the FBRK with this formula from Johansen. So failure mechanism A, we find 10 kilonewton, which will be. Then, failure mechanism B, we find 20 kilonewton. Failure mechanism C, we find 22 kilonewton. Failure mechanism D, we find 9.9 kilonewton. Failure mechanism E, we find 17 kilonewton. And failure mechanism F, we find 20 kilonewton. Okay? Now, one question for you. What kind of, do we comply with this provision here? In this way? So are we sure that if we get this number here, our connection will be a dissipative connection? And which value of Q factor should we use? So, any comment? So, are we getting a dissipative connection or non-dissipative? So, are we getting a non-dissipative, dissipative, or very dissipative connection in this case? Dissipative. Why dissipative? Because I take the minimum, and the minimum was 9.9 kilonewton, and this one is D. And D, as you can see here, D is well, D will be this one. Is a dissipative one. Okay? However, do you think it's enough to have a difference between 9.9 and 10 to make sure that we have a dissipative connection? No, they're too close to each other. There are such unknowns and scatter values that if they are so close to each other, it's very likely, or at least it may be likely that also the A occur. The A is not dissipative. So how should we make sure that the connection behavior is really dissipative? by ensuring that there is a certain difference between the two. For example, 20% difference. So, if I want to be sure that this is the failure mechanism occurring in reality, I need to make sure that this one is at least, I would say, 20% less than this. So at least I would say 8 kilonewton. If it is 8 kilonewton, then you see it's 8 kilonewton, so the minimum it's actually 20% less than the other, so I'm fairly sure that that actually this one will occur and not the other. So for this reason, the new regulation, the new Eurocode 8, there would be a provision like this, saying that if I design a dissipative connection, I need to take the minimum among all 3 dissipative failure modes, and this minimum shall be less than or equal to the minimum of the non-dissipative failure mode, using, however, a safety coefficient, kind of safety coefficient. This one is called overstrain factor, takes into account the scatter, and in this case it's 1.2. Okay? Just to make sure that we don't get to this situation that we get before. 9.1 is less than 10, so we say, okay, I'm happy because it's dissipative, but 9.9 and 10 is only the same. So this 9.9 should be at least 8, so this should be at least a factor 1.2 between the dissipative and the non-dissipative failure mode. Okay, it's clear? So this one will appear in the new Eurocode 8. So far, if you look at the technical regulation for construction, Italian one, you don't find this. But please keep in mind that if you use now the technical regulation for the Italian technical regulation for construction, which says that you can actually do a design like this, please take this safety coefficient, because otherwise you may end up by saying that in this case here, 9.9 is fine, while 10 is not because we go to the other. Okay? It's clear what we are talking about? Okay. So you see, this is taken from NDC 2018. First, we have this slenderness ratio that we saw before, and then there is in alternativa reazione qui sopra the mechanical connection should be designed to ensure the development of at least one plastic hinge. They don't say that there must be this safety coefficient 1.2. They just say to make sure that you have at least one plastic hinge in the fastener. But to make sure that you have at least one plastic hinge in the fastener, you need at least to make sure that you have a safety coefficient 1.2, because otherwise, if the value are too close, you cannot be sure about this. Okay? So again, why do we want to have a formation of 1 or 2 plastic hinges to the fastener? First of all, if you remember, we said that when we do a test like this, so we pull here a dowel into a timber member, we can get different failure mechanism. The only ductile one is the one characterized by crushing, all the other are brittle. So all the brittle modes, again, you see, all the brittle modes should be characterized by a strength which shall be greater than the strength of the ductile failure mode times the overstrain factor. In this case, since these failure modes here are very brittle, those, in this case, we have to use an overstrain factor of 1.6, no more 1.2. So 1.6 because those splitting and tear out and shift lag and so on, they're very brittle. And if you are in the dissipative zone, we said it's not enough only crushing, but we need to have also at least one plastic hinge formation in the fastener. So we need at least one plastic hinge formation in the fastener together with crushing failure of timber parallel to the grain at the interface with the steel fastener. Why is that? You see here, when we do reverse cyclic loading, as we said before, we get this kind of curves. And the reason why we have this different value of stiffness is that you see in this branch of the car, our fastener, which has one plastic hinge here, one plastic hinge there, is going to be in contact with the wood. So here we have a high stiffness because the dowel is in contact with the wood. When we download, at a certain point, this fastener will lose the contact with the wood. So again, as we push the fastener into the wood, we get a plasticization of the wood. So we get something like this. You see here? This is the hole. This is the dowel. The dowel is being pushed against the wood, so here we have plasticization, and here we have a gap now. So when we push in this direction, we have a stiffness, so we have a contact. When we download and we apply the reverse load, before this dowel goes in touch with the other face, there are some displacements where this dowel is in between the holes, so it's not in contact anymore with the wood. So we are in this zone here. So here is in contact, high value of stiffness. Here we download, is still in contact, but then this one goes in the middle of the hole. It's no longer in contact. You can see that here we have this lower stiffness because there is no longer a contact between the steel and the wood. Then we pull on the other direction, it gets again in contact with the wood, so again higher stiffness, and then we download and again move in this direction here, no contact anymore, and reduce stiffness. Okay? So the branches of the diagram characterized by reduced stiffness are those where we have no longer a contact between the dowel and the wood, due to the timber plasticization around the hole. If we have a plastic hinge formation like here, we have 3 plastic hinge formations. As you can see here, we have lots of energy dissipation. If we oversize the dowel, so we don't allow the steel to plasticize, then as you can see, we have much less energy dissipation. So the restorative loop are much tighter, meaning that we have less energy dissipation and less value of the barrier factor. Of course, ideally, if we can exploit all the plasticization of the steel, for example, by building this kind of dome steel plate, which is then welded to other 2 steel plates which are nailed to the timber. In this case, all the plasticization of the steel, so in this case, let's say that we have the plasticization of the steel of this dome bond. In this case, we can maximize the energy dissipation. So in this case, we have a very fat isolated loop characterized by lots of energy dissipation. In this case, what we would be doing here, we would design this nail steel to timber connection for the overstrength of the steel. So we will make this connection here very rigid in order to make sure we have no plasticization in the nails, and all the plasticization is inside this dot bond steel plate. Okay? But usually, the situation that we have in normal timber structure is this one. So we design dissipative connections by making sure that the steel fastener is plasticized, and then we have a significant amount of energy possible in the joint. Okay? Perhaps not as much as here, but still enough to get some higher value of the barrier factor. So just a reminder that with the Euro-qualified formula, we can actually calculate the dissipative mechanism. If we are in a dissipative connection, we can avoid the dissipative mechanisms characterized by no plastic hinge formation. And we can instead impose that we have at least one plastic information for dissipative connection or more than one plastic information for very dissipative connections. Just remember to use these factors of 1.2 between the failure mode characterized by plastic information and failure mode characterized by only crushing, only embedding. Of course, this coefficient is the same for all the different kind of connections. Also in this case, if we have a steel to timber nail connection, we want to ensure that we have at least one plastic information, so the failure mode B, or if we have a thick steel plate, one or two plastic hinges in the nail. Otherwise, if we don't have B, D, or E, we can have different kind of failure mechanism by brittle. So in all this kind of failure mechanism, always remember to use this 1.2 factor between the brittle and the ductile failure mechanisms. Another important one coming from the regulations: what kind of safety coefficient, partial safety factor to use in design verification. The regulation said that for ultimate state verification of structures designed in accordance with the concept of non-disciplinary structural behavior, so the activity class law, like in the case of your design, of the single-story industrial building, the partial factors for material properties gamma n for fundamental load combination apply. So in your case, you should be using the gamma n factors coming from the NTC 2018 for fundamental combination, which are 1.5 for solid timber and 1.45 for glulam timber. Suppose you are using glulam timber for your building, so 1.45. Okay. For ultimate state verification of structures designed according to the concept of dissipative structural behavior, so that being class M or H, the partial factor for material properties for accidental load combination apply. Now, if you look at the Eurocode file, for the partial factor for accidental load combination, gamma m is equal to 1. Okay? However, if you look at the NTC 2018, our Italian regulation, they said that you can use 1 only if you take into account the reduced strength inside the condition. So only if you reduce the strength and take into account the strength degradation, you can use the behavior, you can use the gamma n equal to 1. Since in general we don't do so because we calculate the strength of a connection, for example, using the Johansen equation, and those Johansen equations do not consider any strength degradation. According to our technical regulation for construction, we should be using 1.5. So in the end, in Italy at the moment, we should use 1.5 for both non-dissipative and dissipative design. Okay? And then you see that the Eurocode said that in order to ensure the development of cyclic yielding on dissipative zones, all other structural member connections shall be designed with sufficient overstrength. So this concept of overstrength is mentioned. Particularly, you say, well, unvoltized and any connection to massive sub-elements, for example, the all-down can be considered as an unvoltized, and they said that this must be overstrong. And also connections to horizontal diaphragm and lateral load resisting vertical elements. So, now we need to understand, and here we need to be careful, so please try to follow what I'm saying now. If you don't understand, repeat, because this is really tricky now, this concept of capacity-based design in general, and particularly capacity-based design for infrastructure. So far we have learned capacity-based design only from the course in reinforced concrete design, where I think it was designed quite properly. But we need now to understand perhaps a bit better the application of capacity-based design to a timber structure. So suppose that you have to design this connection, this dissipative connection between this column in this field. So you have a non-resisting frame like the one that you are designing, your course, your design. However, in your case we said for simplicity you consider it as a non-dissipative one. Now suppose that we want to consider this design as a dissipative one. How should we be designing this connection here between the timber beam and the timber column? Well, we should first calculate what we call the seismic design, the seismic demand. The seismic demand will be a bending moment here. It will be a kind of bending moment for the beam and a torque moment for the connection. So this torque moment for the connection, seismic demand, LPDE, should be calculated by analyzing the frame under some equivalent seismic forces calculated using the design spectrum. So exactly like you did for your moment-resisting frame made of reinforced 2 years ago. So you calculate, you design, in this case, not the joint, but the bending moment of the beam was designed by analyzing the frame under a system of equivalent lateral forces calculated using the design spectrum. Design spectrum, which is taken from the elastic spectrum and dividing it by the Q factor. In your case was 5. In this case could be, for a joint like this, it could be 4. Okay? It's clear? So, when we have to design this beam column joint, we need to calculate the size of the demand LPDE by solving the frame under a system of equivalent seismic forces calculated from the design spectrum. The design spectrum is the elastic spectrum divided by the Q factor. This case will be Q factor of 4. Okay? So we do this analysis, we calculate the seismic demand LPDE. We need to compare the seismic demand with the capacity of the joint. Okay? Assuming that this is a big dissipative joint. So the capacity of the joint can be indicated by FRDD. So this is the capacity, the bending capacity, or the torsional moment capacity of a dissipative joint, FRDD. Now, if this is our frame, we know that the joint is the only dissipative component of the frame, while instead the timber column and the timber beam are the brittle components. Okay? Of course, this is different from what you learned for reinforced concrete, because for reinforced concrete, what would have been the dissipative component in reinforced concrete design? Which component was the dissipative one? Not the steel, because the steel was a part of I'm talking about the component now. What was it for reinforced concrete? What was the dissipative component? The joint, the column, or the beam? The beam. So, in reinforced concrete, this one, not the whole beam, but let's say the section of the beam close to the joint was the dissipative component. So we were designing this for the seismic demand. While instead, the column and the joints were the brittle component, and we were designing them using capacity-based design. In this case, instead, the connection is the ductile component. We designed the connection for the seismic demand, so for the basically for the seismic, what we call for the design spectrum, which is the elastic spectrum divided by the Q factor. Okay? What does it mean that we design this for the design spectrum? It means that we need to make sure that the capacity of the joint itself, so the moment resisting of the joint, FRDD, shall be greater than or equal to the seismic demand calculated using the Q factor of 4. Okay? So this is the ductile, so the dissipative component, while instead beam and column are the brittle elements. Okay? So, if now we use the distribution of the demand and the distribution of the capacity, if you remember well, we discussed this in the reinforcement design, the loads and also the strength are always regarded in this semi-probabilistic linear design method as functions that are normally distributed. So we always assume that both the demand and the capacity, they are not only one value, but they may be characterized by a certain probability density function. So, in terms, for example, of seismic demand, the seismic demand won't be a fixed value. The seismic demand, so the bending moment in this joint here, will have some coefficient of variation. It will have a mean value. They will have a normally distributed function. There will be a value between two limits. In general, if you remember, when we define the characteristic value of the load, we make reference to which value? To the mean, to the lower fifth percentile, to the upper fifth percentile? To the upper fifth percentile. Because we want to make sure that the probability to exceed, the probability of that the actual load exceeds this value is very low, 75%. Okay? So, FVDE, the seismic demand, the bending moment that we are designing for this connection here, will come from the upper fifth percentile down from this curve, which is actually calculated from, we said, the design spectrum. This comes from the elastic spectrum divided by Q. Okay? So this is our design value. And then, of course, we have the actual strength capacity of the joint. Is the actual strength capacity of the joint only one value? No, it has a scatter of values. Okay? Again, a function like this. Normally distributed, for example. Also here there is a value, an upper fifth percentile, and lower fifth percentile. Now if we want to be sure with a certain probability of certainty that my joint doesn't break, I will have to make sure that the lower fifth percentile divided by a certain safety coefficient will be greater than the upper fifth percentile of the demand. Okay? So, if this is the distribution of strength of the joint, there will be a mean value. There will be a characteristic value, the fifth percentile, lower fifth percentile, and then there will be a design value obtained by multiplying the characteristic value by K mod, multiplication factor, and divided by the gamma n factor. So, our designing equality in the joint, the dissipative component, will be that FRDD, design strength capacity of the joint, which is the characteristic strength capacity times K mod divided by gamma n, shall be greater than the seismic design. FVDE, okay? Where FVDE has been calculated from the seismic, from the design spectrum, which is the elastic spectrum divided by Q factor, where Q factor is equal to 4. Okay? So it's clear until here that the design of the dissipative component. Okay, until here there shouldn't be any important news with respect to what we do. Now the news comes from how we design the brittle component, the brittle member. So how do we design the basically timber beam and the column beam, the timber column? Both of them, you see, they are brittle components. What does it mean they're brittle component? It means that if they break, all the structure will break, and there will be no possibility for this joint to dissipate energy. Just a reminder that the only reason why we are able to reduce the seismic, the elastic spectrum by the Q factor is just that we make an assumption that this joint here is going to dissipate energy. This joint should have, if we have a, let's say, M over rotation, so baby moment over rotation for this joint, this should have something, should be something like this. So it should be characterized by a significant energy dissipation. Only if we have this energy dissipation, we can use a Q factor of, let's say, 4 in order to calculate FVDE. Okay? But to have a dissipation of energy, first of all, I need to make sure that this connector can plasticize. This metal connector, they have to be able to plasticize. So they have to form one or two plastic edges. But secondly, most importantly, I should avoid any brittle failure outside the connection region. Because if I have a brittle failure on the beam, immediately after this brittle failure, the structure will break and we won't have any possibility of dissipate energy to the joint. Because as you can see here, the system is like a chain made from different links. If I break, let's say, the brittle link, immediately I break everything. Okay? So the prerequisite to be able to design this joint for the reduced seismic demand, so FVDE, is that the joint can dissipate energy. How can I be sure that the joint can dissipate energy and that these brittle elements won't fail? So, I will have to study for which demand do I need to design the beam. Can I design the beam for the same demand as the joint? So can I design the beam, also the beam for FVDE? If I design the beam for FVDE, so for this value here, it means that for the beam, I could have a strength which could be like this curve here, like the red one, right? Suppose that I consider as a demand in the beam FVDE. Okay, I design the beam for the same moment as the joint. If I do so, it means that I will get a beam with a curve which will be, let's say, more or less like the curve of the joint. So I will just need to make sure that FRD of the beam shall be greater than FVDE. It means that I will have the same probability that I have a failure in the joint and that I have a failure in the beam. But if the probability is the same, I could say that in 50% of the cases I will have a break in the beam, 50% of the cases I will have plasticization in the joint. Is that okay? Would that be okay to assume that in 50% of the case the beam is going to break? No, because in one structure out of two, I will have a break in the beam, which means that my design will be completely wrong. In fact, if I had a break in the beam, which value of the Q factor should I have used before? Remember what we have done. We used Q factor of 4. With the Q factor of 4, we calculated the reduced seismic spectrum. And so we calculated FVDE. And then we use FVDE to design the joint and to design the beam. But if the beam, we said, if the beam 1 in 2 structure, if we have that in 1 in 2 structure, the beam breaks, it means that basically I cannot have this plasticization. We said we can have this plasticization only if the beam doesn't break and if this connection is going to plasticize. Okay? So if the beam breaks, which value of the Q factor should I have been used to design the joint and the beam itself? In case of the brittle failure of the beam, which value of Q factor should I have used? No? Right here? Now, let's think about it. You have a structure in the structure, rather than having this ductile failure, you have a brittle failure. So you have no energy dissipation, because if the beam breaks, it means that you cannot dissipate any energy here. So in the end, you have no energy dissipation. If you have no energy dissipation, which Q factor should be used? If you have no energy dissipation, theoretically, what is the value of the Q factor? If you have no energy dissipation at all, 1. The regulation said, okay, you can use 1.5 because anyway you have a little bit of strength always. So, if we were to design the beam for the same bending moment as the connection, so it means that we have the same probability of failure on the beam in the connection. In this case, to be correct, we should have designed the beam and the joint not for the design spectrum, but for the elastic spectrum. So, for the spectrum obtained, if you want, by dividing the elastic spectrum by 1.5, not by 4. Okay? It's clear so far? Because it's a bit complex, this concept, particularly if you speak in English. Have you understood? So, now the question is, for which demand should I design this beam to make sure, with an acceptable probability, that I will have the plasticization of this rather than the failure of the beam itself? So, let's try now. Since the bending moment for the equilibrium, the bending moment in the joint is exactly the same as the bending moment in the beam. Okay? They are exactly the same. Now, in terms of demand, in terms of capacity, if I consider now like load, no longer the actual value of the seismic demand in the joint, but the upper fifth percentile of the actual strength of the joint. So if I now am going to consider this as a load, if I make sure that, so if I consider, you see, as a load FR095D, so I'm considering now as a load for the beam, no longer the actual load in the joint, but the actual the upper fifth percentile of the actual strength of the connection. Because the strength of the connection, we say, is not a one value. It has a curve, it has a distribution. Now, in which case I would be almost sure that the beam is not going to fail before the joint. If I design the beam for the upper fifth percentile of the strength of the joint. So, you see, the joint has this kind of, the joint can have a variable value of strength between those 2 points. Of course, theoretically, I should design for an infinite value, because theoretically, I know with very low probability, this joint may have an infinite resistance, but this doesn't have any physical sense. So, if you want to be quite sure that the beam is not going to break before the joint, I could design the beam for the upper fifth percentile of the strength of the joint. So I take, you see this value, FR095D. This is the upper fifth percentile of the strength of the joint. And I take now this as a strength demand for the brittle component. So strength demand for the beam, which is the brittle component. So now, my strength capacity, FRDE, the strength capacity of the beam, shall be greater than or equal to no longer FRDE or FVDE, but FR095D. So in other words, you see now, the beam will have another distribution of strength, this blue curve. So this is the distribution of strength of the beam, which will have a fifth percentile, FRKD, and the design value, FRDB. So the design value of the brittle component, as usual, will be given by K mod times the characteristic value of the brittle component divided by gamma m, And this value here, FRDB, shall be greater than or equal to no longer FVD, but you see, gamma RD over strength factor times FRDD, where FRDD is the design value of the strain capacity of the joint. Now, gamma RD is the overstrain factor, and FRDD is calculated as usual with the formula K mod FRKD divided by gamma N. Now, what is the overstrain factor in this case? Graphically, gamma RD is the distance, as you can see here, between the design value of the strength of the joint and, if you want, and what we call the upper fifth percentile of the strength of the joint. So it mostly takes into account the gamma RD, mostly takes into account the scatter of the joint strength. So if the joint strength was not a probabilistic value but was a deterministic value, then you can see gamma RD will become basically 1. And then we could have the superposition between the, well, not the superposition, but this blue curve could replace the red one, because the red one would deform into a vertical line. Okay? So in other words, the overstrain factor mostly takes into account the scatter of value of the strength value of the connection. So in the end, we end up by saying that capacity-based design will be applied exactly like you did for reinforced concrete. In this case, gamma D is mostly, now we see there are also some components. In this case, gamma D is mostly the scatter of values of the strength of the dissipative component. And in the end, it's in some way, gamma D is the ratio between the upper fifth percentile and the lower fifth percentile of the strength of the connection. Okay? Now, is it clear why we want to design for this value here rather than for the other one? Do you have a question about this? So this is a fairly complex concept, which is actually the same for all materials. The only important difference is that for timber, this curve is quite flat. So we have an important scatter of experimental values. When instead for steel, this curve here would be much narrower.
Scusa, questa è una domanda, ma il prodotto gamma RD per FRDD sarebbe 0,5D.
This one, gamma D times FRDD, this is exactly, yes, we could add it maybe for the sake of clarity. Yes, this is FR. Let me think, is it exactly FR? FR 095D. Yes, FR 095D is exactly the same. We can add it, so we make it even clearer. Okay? Any questions? So this is basically what we said before, is the summary. The dissipative zones, which are selected timber connection, timber structure, are designed for the reduced seismic actions calculated considering the behavior factor Q, assuming gamma m equal to 1 according to VC rate, or gamma m greater than 1 for fundamental combination according to NTC 2018. So this means that when we design cross-line structures, we design for the reduced seismic actions only. You remember what? The cross-line building. Which connection are we going to design for the reduced seismic spectrum? Yes, I'm just asking for a cross-line structure. When you design the cross-line structure in earthquake-prone area, which connections will be designed for the reduced, for the design spectrum, basically, so for the reduced elastic spectrum, which is elastic spectrum divided by 1 by 4 by Q factor. Only some connections, we said, not all the members. Remember which connections in a cross-line panel, in a cross-line structure? We said the nail of the screw connection between adjacent panels, in order to allow this kind of behavior, so this vertical here, and the connection between the old downs and the timber, and the connection between angle brackets and the timber. Okay, only this will be designed for this reduced factor. In a lifeline structure, only the nail connection between the sheathing and the frame. Okay? Okay, everything else will be designed using capacity-based design. So will be designed with this criteria that we saw before. So meaning that, you see, we need to multiply. We need to start from the actual design strength of the dissipative connection, like it was the bending strength of your frame, if you remember. We need to multiply this by the overstrength factor, and then from the equilibrium we need to find out the other values acting from the equilibrium your members. So in this case, it is ensured that the failure of the brittle parts will not occur before the crystallization of the ductile connections. Because what we have done this way, we have strengthened the brittle connection. We have oversized the brittle connection. We have oversized it in such a way to be that we are in such a way that the probability that these brittle members can fail is only 55%, because we have designed for the upper 50%. Okay? So, now if you look at the overstrength ratio, we said before that the most important component of the overstrength ratio is the scatter of the results. In the reality, it's not only the scatter. Now, suppose that you do a test like this. So you have a timber connection, you apply a load, and you go up to the failure of the member. In the end, you get a curve like this. If you repeat the test with more specimens, you get a certain scatter of results, as you can see here. So we would have for example, 5 different curves with different value of results. And of course, if you have here a number of results, you can always calculate the mean value. You can always calculate the upper 50th percentile and lower 50th percentile. Okay, of this connection here. Now, if this is the dissipative connection in our structure, we can say that the demand due to the seismic action, so the seismic design, shall be less than or equal to, in general, the analytical design value of the connection itself. So, FD is the strength demand calculated using the reduced reduced elastic spectrum, the reduced design spectrum, which is the elastic spectrum divided by the factor. And then we will have a design strength. In general, these two curves, they are not always superimposed. So the actual size of the design, the size of the demand, is usually less than the actual capacity. Why is that? Because, for example, when we design a nail connection, in order to get the equality, it would mean that we have to use some spacing like 3.93 millimeters. Okay, not to get the equality. Or we would have to use some diameter like 4.5 millimeter diameters, dowels. While instead, we know that the dowel, like this one, it can be either 10 millimeter or 12 millimeter or 14 millimeter. We cannot have 12.1. So in general, we have always that this one is an inequality. So meaning that there is a difference between the actual demand and the actual strength. This difference comes from the fact, as I said before, that we cannot really have dowels which have some kind of decimal points or spacing which are 7.2 millimeters. We always use round number. So from the round number it comes that there is always a difference. So this difference between the capacity, the actual capacity, and the demand is called over-design factor. For example, you design a nail connection, you find out that in order to get this design inequality and inequalities, in order to get the equal sign here, you need to use nails 3 millimeter diameter every 88.9 millimeter. Okay? So 3 millimeter diameter every 88.9 millimeter. In the reality, you can't put 88.9 millimeter. You need to say, you need to round it. You can round to 90. No, because it's if you increase the spacing, it means that you have less strength. So the spacing must be lower. So 88.9, you can round to 85. You can say, okay, I use 3 millimeter nail every 85 millimeter. The over design in this case would be 88.9 divided by 85. So you get an over design factor of 1.05, 1.06. So this is called over design factor. And then we calculate the over design factor as the ratio between the design value of the analytical strength and the upper 5th percentile value, or if you want, the lower 95th percentile value. So the over design factor gamma D is FV095 experimental, so this one, divided by FVD analytical. Well, FVD analytical for a connection like this would be basically the formula from the Eurosol 5 saying that the capacity is K mod times the characteristic analytical value of the shear strength divided by gamma n. Well, gamma n is the partial factor. So, if you want, this ratio here can also be put as a product of 3 different ratios. So it could be FVK analytical divided by FVD analytical times FV 0.05 experimental divided by FVK analytical times FV 0.95 experimental divided by FV 0.05 experimental. So what does it mean? It means that from basically the analytical prediction of the capacity of the strength of this connection, I can move to the analytical prediction of the characteristic strength. So the difference between these two is basically, if this is FPK analytical, the difference between the black line and the yellow line is basically gamma n over T mod. So it's just this safety coefficient, gamma n over T mod. And then there is a difference between the analytical prediction of the shear strength and the experimental prediction, or if you want, the experimental measure of the characteristic strength. So the difference between these two values here is due to the fact that when I use the Johansen equation, with the Johansen equation I approximate in some way the value of the experimental test. So the Johansen equation are an approximation of the experimental value of the shear resistance. So there is a difference between these two. Usually, the Johansen equation are conservative. So this ratio here, gamma AN, is usually greater than 1. And then at the end, as you can see, I have a difference between the lower 5th percentile and the upper 5th percentile, or if you want, the lower 5th percentile and the lower 95th percentile. And this difference here, that we can indicate with gamma scatter, this really depends on the scatter of the material. For example, when you design a steel structure, this gamma SC is very little, it's almost 1. Because for steel, the difference between the lower and the upper 5th percentile is very low. However, for material like concrete, but particularly like timber, this one becomes the most important component. So this is why before, in the plot that we saw before, I just put gamma, I just put this member here, because this was the most important one. There is not only one, you can see, there are 3 ratios, okay, which contribute to the value of the overstrength factor. So in the end, what we should really remember out of this lecture here, is that there is an important difference between the analytical prediction of the strength capacity of a connection and the upper 5th percentile, experimental 5th percentile of the connection itself. This difference is called overstrength factor. It's actually not a difference in the ratio, but it's called overstrength factor. And we have to use the overstrength factor the same way as we use the overstrength factor when we design our moment resisting frame in reinforced concrete. Just in this case, you have to remember that the dissipative element is the connection, not the joint. While instead in the other case, the dissipative element was the beam, not the joint. Okay? In this case, it's the connection, not the beam. Sorry, I said the connection, not the joint. In this case, the dissipative element is the connection, not the beam. While instead for reinforced concrete was the beam, not the connection. Okay? Now, which value to use for the overstrength ratio? If you look at the Eurocode 8, in the current version of Eurocode 8, there is no indication about the value for the overstrength. If you look into the Italian regulation from 1.3 to 1.6, like in the new draft of Eurocode 8, the New Zealand standard is 2. So as you can see, the value is significantly higher than the value that you have used for your design. Because we said before, for reinforced concrete was 1.5, for steel is even less. Here is either 1.3 or 1.6. You can see here, Italian regulation, overstrength factors for the activity class A, which means highly dissipative structure, 1.6. For the activity class B, which is medium dissipative structure, 1.3. And similar values you can see in the new Eurocode 5, Eurocode 8 draft, which is still under discussion, 1.3 to 1.6. These values come from the results of several experimental cyclic tests that were performed in different research institutes in Europe and around the world. You can see here several cyclic tests under brackets in the axial direction, in the shear direction, so on. So several tests, and in the end, those were the values that were found. So, in the end, when we do our circuit design, we will proceed in this way. First, we are going to see, depending on the structural system, from the table of the behavior factor, which value of the behavior factor we can assume. So, if our structure is medium or high density, we get the value of the behavior factor. Then, we consider the design spectrum, which is obtained by the elastic spectrum divided by the Q factor. With this value of cyclic action, we go to design the dissipative elements. Once we have designed the dissipative element, we use capacity-based design to design all the brittle elements. Now, what are the dissipative elements and brittle elements, for example, for cross-line buildings? We already said before, but now we can summarize better. So, capacity-based design rule for cross-line building, which are under development in the new generation of Eurocode 8. Extant timber buildings shall act at the greater possible extent as box-type structures. We are going to study next year about, in the course of masonry construction, that in order to get very good behavior from the masonry structure, the only way is to make sure that this masonry structure will behave as a box-type of structure. What does it mean, box-type of structure? You know, if you have, for example, a box where you put your shoes, if you have a box without the lid, you know that the resistance is much lower than if you have a box with the lid. Completely different. So, a structure like this. So, a box with the lid is much weaker compared to a box with instead a lid above. Okay? So, the idea is that both light frame structure and cross-line structure should behave at the greater possible extent as a box-type structure. So, we say in a cross-laminated timber buildings, what are the dissipative connections? So, if this is the structure, made you see with shorter panels. So, the wall is made from shorter panels. Then we have the floor member from other panels. So all the vertical screw joints between wall panels, one indicated in blue, will be dissipative members. Also, you see this kind of joints here, screw joints. Also, the nail connection between the angle brackets and the wall panels. Also, this nail connection will be dissipative joints. And also, the nail connection between the hold downs and the panels. So, those three kind of connections are the dissipative connection in cross-laminated buildings. And they will all be designed for the reduced elastic spectrum. So, for the elastic spectrum divided by the Q factor, that according to the Italian regulation is equal to 2.5. Okay? Okay. In order to ensure the development of the cyclic yielding in these dissipative zones, everything else shall be capacity designed. What does it mean? That all the other members will not be designed for the same cyclic forces, for the cyclic forces obtained from the design spectrum, but will be designed for the overstrength of these dissipative joints using equilibrium. Okay? So, connection, first of all, some of the connection will be designed for the overstrength of the dissipative zone. So 1.3 is the overstrength factors according to Italian regulation. For example, you see here the screwed connection between adjacent floor panels. This screwed connection will be designed for the overstrength of the other connection. Okay? So this connection, screw connection between floor panels will be designed for the overstrength of the other connection. Also, the screw connection between the floor panels and the walls will be designed for the overstrength of the other connection. And also the corner connection. See this corner connection, or the connection between the walls and perpendicular walls. Those corner connections, together with this connection between, let's say, the lid of our box and the wall of the box, all these red connections, we have to be over-designed. Make sure that this box type, this box shell, is retained during it doesn't have out of plane failures. Okay? Note that in the dissipative connections, in order to get activity, we will have to use always fasteners perpendicular to the shear plane. So, if we go back, this is a very important point. So, in this connection here, in order to get dissipative behavior, we will have to have, for example, this is the typical connection between adjacent walls with LVL screws, for example. Okay? Or you can have a joint like this. Okay, this connection, to be dissipative, will have to have fastener applied perpendicular to the shear plane. Okay? So the fastener shall be perpendicular to the shear plane. The same thing also in this net connection between the under brackets and between the all downs and the walls. So all those connections shall be made by fastener with a direction perpendicular to the shear plane. Okay? And since those are dissipative connections, we will have to make sure that the failure modes of those screws or joints are characterized by at least one plastic hinge formation. Okay, it's clear what I'm talking about? Instead, this other connection you can see here, so the connection that are to be designed for the overstrength of the other, for this connection we are not interested in ductile behavior, because those are connections that may also be hard to break. So for this connection, the best way is to use inclined screws. So in this case, we can use inclined screws, so not perpendicular to the shear plane, but inclined, 45 degrees. Because when we incline the screws, if you remember, we increase both the strength and the stiffness. However, we cannot use inclined screws in the dissipative regions. Because in the dissipative regions, if you remember, the inclined screws that only have very ductile. They're very strong and stiff, but not ductile. Okay? In addition, we said all these connections will have to be oversized, so designed for, we're using capacity-based design, so designed for the overstrength of the dissipative joints. And also some other members, for example, the panel itself behaves brittle. So also the panel will have to be designed for the overstrength of the dissipative connections. and also the floor panels. And also you see the metal part of the hold downs. So this is a photo showing a kind of wrong failure mechanism. This is actually a real hold down that was tested by a former PhD student of mine, and he found out, you see, that this hold down broke in this way. Now this is a clearly wrong failure mechanism. Why is it a clearly wrong failure mechanism? Because we said before that the hold down shall be designed in such a way that this nail connection can plasticize. Because all the energy dissipation comes from the failure of this nail connection between the hold downs and the timber itself. If there is a failure like this, it's clear that this connection cannot dissipate energy. It's clear that the system becomes unstable, and it's clear that we cannot design a system that breaks in this way for a Q factor of 2.5. We should be designing for a Q factor of no? 1, should be 1, but at least 1.5. Okay? So, why was this hold down designed this way? Because originally this hold down here was not developed by the producer for cross-lamp buildings, but for light frame construction. We will see that in light frame construction, the hold down in general should not dissipate any energy, because we said that for light frame construction, the only member dissipating energy is the nail connection between the sheathing and the frame. Everything else, including the hold down, should be oversized. So this hold down was designed, actually was designed for a light frame structure, so it had a lot of holes. So if you fill all the holes with the nails, you can get that this nail connection is much stronger compared to the tensile strength of the net cross section of the hold down itself. So in other words, this hold down has too many holes and is too slender. In order to have a right design, it should be either less holes or thicker, in order to make sure that the strength of the net section of the plate should be greater than the strength of all these nails. Okay? So also these metal plates of the hold down should be designed for the overstrength of the connection itself. And also you see here, this screw connection of the under brackets to the floor should not break this way. So let's say that the strength of this part should be much larger than the strength of this part here, which is the ductile part. So also this was not designed properly. So all of those figures, those photos shows failure modes which are wrong. Why are those failure modes wrong? Because with D, you can see the ductile part of the hold down on the under bracket. So D is the ductile, what we should be designing as a ductile connection. While instead, with B is the brittle part. The brittle part can be the connection or can be the metal itself. Now, how to ensure the brittle failure mechanisms B of hold down under brackets won't occur? So how can we make sure that hold down is well designed? So how can we make sure that the brittle part won't fail before the ductile part? We need to use also on the hold down what we call capacity phase design. So if we indicate with Fd the strength of this part, we should make sure that the strength of this part, Fd, is less than Fp. But it's not enough that Fd is less than Fp. Fd times an overstrain shall be less than Fd. So, something like this. So gamma D over strength times FRBD, which is the strength of the ductile part of the hold down of the bracket, should be less than FRDD. So the strength of the brittle part. And this applies for the connection, but applies also for the metal part. Like we were saying before, to avoid this failure here, we should say that the strength of the ductile connection times the overstrength, gamma RT, shall be less than the strength of the metal part. Okay? So for the cross stability, we should also do capacity design not only at the building level, at the wall level, but also at the connector level to make sure that those failure mechanisms won't occur. Now, values 1.3 according to NTC 18. Now, last thing, then we finish for today, is capacity-based design at the whole building level. Now, we should use capacity-based design at the whole building level. Why? Because we have our building. The building is subjected to an inverted triangular distribution of seismic forces. The seismic shear has a trend like this, more or less. Now, suppose that, let's do this way. Suppose that we adopt exactly the same strength of each story. So, this is the strength demand. As you can see, we have a larger demand at the lower story than at the upper story, because this is the demand of seismic force. So, what does it mean that we have a larger demand at the lower story? It means that at the lower story we will have to put more angle brackets. Okay? So we need more angle brackets at the lower story than at the upper story, because the strength demand is maximum at the lower story. Now, suppose that for the sake of simplicity, we use exactly the same number of angle brackets along the height of the building. So what does it mean? That this will be the story seismic shear demand in red. If we use exactly the same number of angle brackets throughout the height, we would get in yellow the strain capacity. So the strain capacity would be exactly constant along the whole height of the building. Okay? Now, when it comes to the dissipation of the building, since you see that there is, as I go up with the building, as I proceed on top of the building, the strength is the same and the demand is lower. Where will I get plasticization? If I get plasticization, we get plasticization only on the base. Because on the base I have the minimum, if you want, the minimum difference between strength demand and strength capacity. Well, instead this difference is larger at the top. Okay? So I can get plasticization only on the bottom of the building. But if I have plasticization only on the bottom of the building, you can see that the displacement on the top is only V2. Okay, because I have plasticization only on the bottom of the building. Now, can I improve the ductility of the building? Yes, I can improve the ductility of it. I can improve the ductility of the building if I increase the top displacement. How can I increase the top displacement? By making sure that I have plasticization throughout the height of the building. So not only on the bottom of the building, but I have plasticization on the floor of the building. How can I get this plasticization on the floor of the building? Only if I keep, you see, only if I follow not the yellow one, but the blue one. So if I basically follow with my capacity, the strain capacity, the strain demand. The strain demand is a curve. I need to follow also with the strain capacity the same curve. So what I need to do, basically, I need to make sure that, you see, the seismic resistance of extant mode is higher in the lower story and decrease at the higher story proportional to the decrease of the story seismic shear. In other words, I need to keep constant the ratio between the strain demand and the strain capacity, which means that I have to increase the spacing of the angle brackets as I go along the height of the building. In other words, I need to decrease the number of angle brackets. I need to use more angle brackets here and less angle brackets as I go to the height of the building by keeping constant the ratio between strain demand and strain capacity. If I do so, what is the advantage? The advantage is that I have this time plasticization of all the story, and I have, actually, the final displacement is V1 against V2. Which means that if I have some cycles with V1, I can dissipate much more energy compared to the case with V2. More or less, it's like having on a shear wall, if you have a shear wall, you may have plasticization only here, and then the wall, of course, will have this kind of displacement, or you may have a plasticization throughout the height. And then in this case, you will have a much higher, so you have a plasticization throughout the wall, and then you will have much higher energy dissipation. Okay? So this is another very important seismic capacity-based design at building level criteria that basically can be summarized by saying that we should not keep the strength constant with the height of the building, but we should try to follow with the strength capacity should follow the strength demand. So, which means that if the angle brackets are the resisting member, the number of the angle brackets should reduce as we go along the height of the building, by making sure that this strength capacity curve can follow, can have the ratio between strength capacity and strength demand is the same along the height of the building. Is that clear, this concept? Any questions? This is an important concept, so that
Scusi, perché la domanda invece va durante con l'altezza?
Okay, because we are talking about this is the distribution of forces. It's like having this. So the wall is like a cantilever. So the wall is a cantilever with a distribution of forces in this way. Now, if I ask you to do the shear force diagram, how would be the shear force diagram here? I start from here. One value. Then go here. Value is slightly smaller because I need to add this. Then go down. I need to add this. Go down. This. And this is more or less the curve that I showed before. So this is the distribution of the shear of the seismic, this is the distribution of the seismic forces along the height of the building, and this is the shear force diagram. It's clear? So the shear, if I do this one, if I do a cross section here, this is the value of the shear that I can find in my building. Okay? So we need to be careful not to make a confusion between the seismic force at each floor and the seismic shear. The seismic shear is the result of all the seismic forces that I have above this cross section. And since in a static and the equivalent static analysis you learn that you have an inverted triangular distribution, the seismic shear has more or less this trend.